So thank you, Jaden, and thank you everyone for joining to our student seminar sessions. Today, our speaker will be Jaden from Colorado State University. Jaden works in Professor Jorge Roca's group, and today he'll be presenting on irradiating nanowires with femtosecond pulses of relativistic intensities to generate fusion neutrons. I know there's been a lot of talk, Jaden, about just your work altogether. A lot of people have shown a lot of interest with what you're doing and how you're collaborating with Marvel Fusion. So thank you so much for agreeing to speak today.
Yeah, thanks for having me. All right. So yeah, my name is Jaden Hoechstetter, and I am a second-year graduate student at Colorado State University, studying under Professor Jorge Roca. And today I am giving a talk on irradiating nanowires with femtosecond pulses of relativistic intensities to generate fusion neutrons. So to start off, we are located at Colorado State University, which is in Fort Collins, Colorado. And our lab is at the Engineering Research Center and the Advanced Beam Lab at the Foothills campus, right on the boundary between the Great Plains and the Rocky Mountains. And this is Fort Collins right here, and these mountains in the back are part of Rocky Mountain National Park. And then this is where our lab is located. So at the Advanced Beam Lab, we focus on developing high power, ultra-short pulses, ultra-short laser pulses. And one of our systems is the Advanced Laser for Extreme Photonics, or the ALIF laser, which is right here. And this is a LaserNet US laser. These lasers have the ability to create extreme plasma conditions through relativistic laser matter interaction. And this can lead to ion acceleration and microscale fusion. So for a fusion reaction to occur, two important variables are needed to be satisfied. The first is the cross-sectional area and the velocity. The easiest reaction that produces the most energy is the deuterium-tritium reaction, where the peak ion energy is lower than all the other reactions. And this curve right here shows the reactivity on the vertical axis with the ion energy on the horizontal axis. And you can see the deuterium-tritium line has the least amount of ion energy in order to react. But tritium is very expensive and radioactive. So at Colorado State University, we mostly work with the two deuterium reactions, these two, as well as exploring some of the other reactions, specifically helium, lithium, and beryllium reactions, as well as the proton boron 11 reactions. And although the peak for these reactions is not as low in keV as the deuterium-tritium reactions, they are still in the high keV, low MeV range. So irradiating CD2 with a petawatt laser can create highly energized ions, which can fuse. Irradiating gas, liquid, and solid deuterium targets with relativistic intensities have all proven to generate fusion neutrons or accelerated ions to the energies needed to fuse. People first began exploring this in the late 90s with the development of the petawatt laser, where they would irradiate deuterium CD2 gas clusters and would generate neutrons that way. And then they moved towards solid targets. And we've also worked with liquid water jets, which can ion accelerate. And in this case, be used as the pitcher for a pitcher-catcher regime, where the catcher would be like a beryllium or a CD2 target that the accelerated ions would interact with and fuse and create neutrons. Nanostructures have the advantage for fusion because they absorb more of the laser light than flat targets. And the wires or the nanostructures also act as microaccelerators. Long aspect ratio nanowires have the advantage of absorbing nearly all the incoming laser light and laser energy compared to a flat target, which doesn't absorb nearly as much. Flat targets absorb 30 to 50% of the incoming laser light, and nanowires absorb up to 70% of the laser light. This graph is from a experiment with larger diameter gold nanowires, and here on the vertical axis is the laser energy absorption, and on the y-axis is the normalized surface area. What you can get here is that for the foil or the flat targets, between 30 to 50% of the laser energy is absorbed, while we see a lot more for nanowire targets of various diameters. And visually, you can see this with a nickel nanowire array. So this is what an array of nickel nanowires looks like. It's completely black, so it doesn't reflect very much, versus a nickel foil, which is very reflective. So femtosecond pulses can penetrate deep into the arrays before the nanowires explode, creating a quasi-homogeneous, ultra-hot dense plasma, which can be shown here. And for example, we irradiated an array of nickel nanowires at 5 times 10 to the 18 watts per square centimeter, creating a near solid density nickel plasmas that were ionized to helium-like electronic states. We observed the nickel helium alpha X-ray emission for nanowire targets and compared the emission to flat targets. This curve, the red curve right here, is the nickel nanowire emission, and the blue curve is the flat emission. And you can see the peak of the flat curve is the nickel K alpha line. And then for the nickel nanowires, we observed large peaks from helium-like nickel. And then up here in this corner, it shows a diagram of the, I think, 35 nanometer, 5 micron tall nickel nanowire arrays. More recently, using intensities of 3 times 10 to the 21 watts per square centimeter, we irradiated gold nanowires, creating a near solid density plasma ionized to nitrogen-like states. Again, here's the X-ray emission spectrum of both the flat target, which is the blue, and the gold nanowire arrays, which is the red here. And for this experiment, the nanowire targets were 8 microns of gold on top of 1.5 microns of nickel nanowires. And then the foil targets were 1.5 microns of gold on top of 1.5 microns of nickel nanowires, or sorry, nickel flat. And you can see the X-ray emission is a lot stronger for the nanowire arrays than it is for the flat target arrays. So steady state ionization balance calculations show that to create such a degree of ionization, electron temperatures must exceed 10 keV. And in our highly transient plasmas, electrons acquire MeV energies and rapidly thermalize to temperatures of several tens of keV. And we got nitrogen like gold appears, which is this curve right here, which is greater than 10 keV. So we also measured the depth of absorption of these nanowire arrays by measuring the X-ray emission versus the nanowire size. How we did this is we had greater than 3 microns of cobalt nanowires, and then on top of that, we put nickel nanowires of various sizes and measured the X-ray emission, and found that the X-ray emission for helium-like nickel peaks or plateaus around 3 microns, while the X-ray emission for helium-like cobalt decreases and hits the continuum level around 5 microns of nickel length. So this shows that the rate of helium-like nickel plateaus at a penetration depth around 5 microns. This puts our plasmas in a very unique matter regime. This figure right here shows the plasma parameter space with electron temperature on the vertical axis and the electron density on the horizontal axis. The bottom line right here represents the lower boundary of the high energy density defined by pressure of greater than 1 megabar and energy densities of greater than 10 to the 5 joule per centimeter squared. And this regime is known as the high energy density regime. The next regime up, 3 orders of magnitude higher, is the very exclusive regions of ultra hot density plasmas inhabited by fusion plasmas created by megajoule lasers and by the nanowire plasmas that are less dense but much hotter than the spherical compression plasmas. These extreme conditions can lead to microscale fusion. Intense laser pulses penetrate deep into the nanowire arrays, creating ions with MeV energies, and these collide, which confuse. Using an array of deuterated polyethylene wires, we demonstrated DD fusion and the fusion generation of neutrons. So to generate these plasmas, we use tabletop petawatt femtosecond lasers as opposed to like megajoule and kilojoule laser systems. And the laser starts with a titanium sapphire oscillator. And then we use chirp pulse amplification with neodymium crystals pumped with 532 nanometer flash pumps to create a 30 joule 50 or 25 femtosecond laser. The beam is then focused using an off-axis parabola, giving us a 1 micron spot size. We frequently double the laser light from 800 nanometers to 400 nanometers to improve the contrast because the pre-pulse damages the nanostructures. This laser irradiates the target, first driving the electrons, which drives the ions in a process known as target normal sheath acceleration, and then these ions collide, forming hot neutrons when they fuse. At Colorado State University, we have the ALIF laser, which is a 3.3 hertz, 30 joule, 800 nanometer, 25 femtosecond laser, and we frequency double it to give us 400 nanometers, 9 joules, 25 femtosecond laser pulses. And then when we focus using our F2 parabola, we get intensities of around 10 to the 21 watts per square centimeter. So to fabricate these nanowires, we start with an anode aluminum oxide template, which is a aluminum oxide template that has a bunch of holes because of a charge given through it. And we buy this from a local supplier. And then what we do is we sputter the top with gold and then electroplate nickel or gold or cobalt or whatever metallic solution is through it to then fill in the gaps of the holes. And then we dissolve the template, leaving the nanowire structured. Different AAO pore sizes and densities can make different densities and sizes of nanowires. So we can produce wires of all shapes and sizes within the range of the AAO template. The AAO template itself gives holes from 30 nanometers diameter to 300 nanometers diameter. And here on the top, you can see a nickel 100 nanometer diameter with 9% solid density. And then on the bottom, we have a nickel 100 nanometer diameter with 24% solid density. Depending on how long we electroplate, we can grow wires of different length. So these two on the right are about 3 micron tall nanowires, and these two on the left are about 9 micron tall nanowires of the densities. And we are currently studying how the wire diameter, density, and height affect the laser absorption and the plasma. For larger wire diameters, greater than 300 nanometers, we use an ion-etched polycarbonate template to make the wires. These wires are truly random because of the ion etching, and but over a larger period, they are uniform in density. The fabrication process varies a little bit from the AAO template. Most notably, we dissolve it in chloroform rather than sodium hydroxide. But then we still sputter with gold, electroplate, and supercritically dry. A negative side towards using these templates is it's very difficult to model because of the randomness of the wires. So to create polyethylene or CH2 and deuterated polyethylene CD2 wires, we extrude the plastic through the templates, creating the nanowires. What we do is we stick the polyethylene film on top of our template and then compress it using a plastic stub while it's heated in an oven so that the wires flow, or the plastic flow through the holes, creating the wire. And then we dissolve the template and critically dry, like the other processes. So these nanowires we measured, and we irradiated these CD2 watt nanowires and measured the fusion neutron generation and compared to flat targets. We achieved 500 times as many neutrons with nanowires as with the flat targets of the same material, and achieved 2.5 times 10 to the 6 neutrons per joule of laser energy. And these were measured on time of flight spectrometers. These irradiated nanowires can also act as ion microaccelerators, accelerating deuterons and protons to the energies required for fusion. This interaction can accelerate protons up to 7 MeV and deuterons up to 6 MeV from the normal of the target, decreasing as you move away from the normal of the target. So in this graph in part A, we measured at a what we call 0 because that's the angle of incidence of the light towards the target. And we measured maximum proton energies of 4.5 MeV and deuteron energies of 3.25 MeV. But then when we irradiate it from a 22.5 degree angle and measure normal from the target, we got proton energies of 7.25 MeV and deuteron energies up to 6.5 MeV. We also performed pitcher-catcher experiments using these CD2 nanowires, using different shields of lithium fluoride, beryllium, and boron nitride. And these were also measured using time-of-flight spectrometers. We observed that beryllium gave the highest neutron per steradian per shot with around 5.5 times 10 to the 6. And lithium fluoride and boron nitride also gave high neutron fluxes. To increase the neutron flux, we cut out part of the catcher target so the laser could irradiate through it at a 30-degree angle and measures significantly more neutron flux of 2 times 10 to the 7 neutrons per steradian per shot, which is 2 to 3 times 10 to the 6 neutrons per steradian per joule. And this is for lithium. At Colorado State, we are working with Marvel Fusion to use nanowires as a basis for a fusion scheme power plant. In this experiment that Marvel Fusion did in collaboration with Colorado State at the Aleph Laser facility, we measured boron nitride nanotubes as a pitcher with a boron nitride plate as the catcher, and measured significantly higher proton energies from the nanotubes than we did from foils also made of boron nitride. And these fusion reactions are the ones that Marvel Fusion were looking at through this experiment, also measured with time of flight spectrometers. So we also studied the ion acceleration from the wires themselves. Several years ago, we conducted a particle and cell simulation showing that TNSA occurs from the ions from the front and the back of the target, but also from the charge stepper on the nanowire surfaces. So our claim is that the nanowires accelerate radially from the wires themselves, which then interact and fuse, creating neutrons. To study this, we fabricated nanowire array strips through an extensive fabrication process. Typically, these nanowire strips were 10 microns wide and the wires were 5 to 10 microns tall. In the case of the polyethylene nanowire strips, we made them 5 microns tall and then 10 microns wide. And how we did this is we started with a empty AAO template and then spin coated PMMA before doing UV lithography, creating a 10 micron strip. And then we added the polyethylene film that we extruded through, creating nanowires in just the 10 micron strip array. Uh, for the polyethylene. And then we conducted an experiment to measure the ion acceleration radially, or at every angle, really, of these nanowire arrays. And for this, we had 7 Thomson parabola spectrometers placed around the target. If the nanowires were here, and we irradiated directly normal of the nanowire arrays, and we had 7 Thomson parabolas here, and then we also had CR39 ion trackers with an array of different MEV stopping power filters, also placed around the target. We irradiated these targets with 400 nanometer wavelength and 60 femtosecond pulse duration, which gave us around 10 to the 21 watts per square centimeter intensities. For our first results, we compared the energy spectrum of the protons from the CH2 nanowire array to the energy spectrums of protons for the CH2 flat targets. And we saw significantly more ions from the nanowire arrays than the flat targets, specifically in the laser backward direction, laser backward being 180 degrees, laser forward being 0 degrees. Both these graphs, the energy and MEV is on the x-axis, with the relative ion count on the y-axis. And the blue here is the 157.5 degree angle. Couldn't get 180 because of the OAP was in the way, but you can see that the flat targets only accelerated ions in the laser backward direction, and none of the angular directions. Whereas for the nanowire, the 10 micron nanowire arrays, it accelerated ions in all directions and a significant amount in the radial direction. We also measured the angular proton flux distribution at different energy levels for both the nanowire arrays and the flat targets, with the green corresponding to 3.8 MeV, the blue corresponding to 2.4 MeV, and the red corresponding to 1.4 MeV. And these are the relative ion or the ion counts for all the ions greater than those MeVs. And so on the left, we have the 10 micron nanowire array with the angle and then the amount of ions per millimeter squared on the y-axis. The angles aren't the exact same as the Thomson parabola angles because the CR39 were spaced a little differently from where the Thomson parabolas were. But in general, we get a similar trend where the maximum proton flux was in the laser backward direction, but we also saw significant ions towards the radial direction, the 90-degree direction. And then the slab direction, but no ions in the radial direction. Again, confirming that the nanowires produce ions radially through TNSA. And we also measured the nickel nanowire arrays and compared it to simulation. We constructed 10 micron tall nickel nanowires with 100 nanometers diameter, and then the arrays were 10 microns wide. Here you can see the nickel nanowire target, the ion count on the y-axis versus the angle, and the amount of ions increases towards the laser backward direction, and this agrees well with the PIC simulation on the bottom. And then further on the right, we measured nickel nanowire arrays to compare it to our CH2 nanowire arrays, the 10 micron strip, to measure the radial acceleration. And here we have the ion flux and the angle, and the majority or the largest flux was in the laser backward direction, and that compares well with the PIC simulation, which is right here. And then we also compared the nanowire or the proton cutoff energies from the nickel nanowires and compared it to PIC simulations. And again, we see the largest cutoff energies were in the laser backward direction, and that agrees well with simulation. So yeah, at Colorado State Each process that we do here consists of preparation, experimentation, and analysis. We make all of our samples in-house. Here's a picture of electroplating or dissolving. We also do a lot of machining. We machine all these electron spectrometers or ion spectrometers, as well as a lot of the parts for the target. And we also do a lot of analysis, have to measure the CR39. The undergraduates are extremely helpful when it comes to this. They get trained on fabricating the nanowires and machining or counting the CR39. And yeah. So outside of nanowires, our team at Colorado State is working hard on preparing a new diode laser system for our new Atlas building, which is currently being constructed. They've laid a lot of the groundwork and they're doing construction right now. And this upgrade will have 3 multi-petawatt diode lasers. And it's a collaboration through Marvel Fusion and will be accessible through LaserNet US. So in conclusion, efficient generation of ultra-high energy density matter from nanostructures, irradiating these nanostructures with pulses of relativistic intensities, create ultra-high energy density plasmas with extreme conditions, and these extreme conditions can lead to fusion. We've demonstrated gold plasmas with really high degrees of ionization with nitrogen-like gold emission, and we measured the convergency of optical light into X-rays of up to 20%. We measured increased flux and energy of electrons and ions from the nanowire arrays as compared to flat targets, and generated quasi-monoenergetic neutrons from the DD fusion, and this can be used as a platform for IFE schemes. So I'd like to point out the people in my group, of course, Professor Jorge, and then work with Nishad and Gabby, who taught me how to make nanowires, Aparajit, and Slava, who does the simulations, and of course all the undergrads, and then all those who work on the laser with us. So yeah, that's a presentation.
Well, thank you, Jaden, for an excellent talk. I know we're kind of on Zoom, so not everyone can give a round of applause, but please give a virtual round of applause for our speaker. So with that, if anyone has any questions, feel free to unmute yourself and ask or drop them in the chat. And, Jaden, if you don't know the answer, we'll make a note of it and we can email Professor Roca later and get the answers from them.
Thank you.
Hi, Jaden, can you hear me?
Yes.
Hi. So in your experiment between slab and the nanowires, you don't see any proton yield in the forward direction. Is it because the slab and the substrate of those nanowires is too thick, so that fast electron can't escape and make an electric field to accelerate the ions?
Yeah, so we do see laser forward accelerated protons, but these protons have a lot lower energies compared to the laser backwards ones, particularly because of how thick our substrates are. We were shooting, it was like 100 micron thick substrates with 5-10 micron tall nanowires. And this is something we're looking to improve. There's a thinner substrate.
Okay, thank you.
Jaden, this is Gary Eden from the University of Illinois, and let me at the outset apologize. Somebody is mowing our lawn, so if a broad band of white noise suddenly appears, it's the gentleman on the mower. Let me say you did a great job in presenting your results. I have a simple question. You prefaced your talk by saying that CSU and Marvel Fusion are pursuing this as a different approach to LFE. So if I heard you right, you said that for your experiments with, I believe, 30 joule pulses, you obtained around 10 to the 6 neutrons per joule. Is that correct?
It was a 9 joule pulse, and with the nanowires themselves, it was about 10 to the 6 neutrons per joule.
Yeah, okay. So so what do you think? I'd love to hear your thoughts, your projections or those from the team. How does that appear to you? I know it's still early in the game, so to speak, but how is that scaling with pulse energy? Of course, the results at Livermore at NIF were much higher. Pulse energy is 2.6 megajoules per pulse. So I mean, it seems to me like you're getting a lot of neutrons per joule. But how does that look in the far field, so to speak?
Yeah, this is something that we're definitely working on improving. As far as scaling with laser energy, we had a follow up to our 2018 microscale fusion, 2021 PhysRev, where we did shoot with different joules of energy up to, was it 9 joules, and it scaled pretty linearly with that. But yeah, it's something that we're looking to improve and making a thinner substrate, as well as figuring out which directions the ions are accelerated the most to, and using different pitcher catcher regimes with like having a beryllium or lithium shield could increase the neutron flux significantly.
Right. Let me rephrase my question. I wasn't asking about approaches that you're using to improve the neutron yield, but maybe the yields you're getting now are not that far away from what you need to demonstrate LFE. In other words, is there some calculations that suggest a neutron yield that you need to have to be interesting for LFE? Maybe you're not that far away.
Yeah.
You see what I'm saying?
All
Because
right.
this is a very different game than the long pulse, 10 nanosecond pulse that NIF needs. Do you see what I'm saying?
Yeah, yeah. In terms of the amount of neutrons, if we for DD fusion, you create a 2.45 MeV neutron, which would be around, for 1 joule of energy, that'd be like 10 to the 12 neutrons needed to create ignition.
Oh, okay.
So
Okay, well, what you're saying is that with your results as today, you're within 6 orders of magnitude, which sounds like a big number, but in this game, that's not that far away. So, and maybe with energy, you'll see a strong nonlinearity in scaling with energy. So, yeah. So what I'm saying is this is really exciting, actually. So, thank you very much, Jaden. With that, I'll be quiet.
Can I
Other
try to
questions?
ask
Go
a
ahead.
question? Maybe make a comment. I'm wondering if my understanding is correct, but I thought that this is more of a test bed. Your setup is more of a test bed for basic fusion concepts, not necessarily a configuration where you would try to produce fusion energy, because there is no target compression here. You would, if you were wanting to produce ignition and fusion energy, you would do something very, very differently, right? So this is not necessarily the goal in these experiments. So I wonder, my question would be, where would you need to go from this configuration toward an arrangement where you can have ignition and fusion energy?
So we're very early in the IFE lifetime. Um, of course, NIF have shown ignition with their megajoule shock compression pulses. But here at Colorado State, we're more studying on different schemes to generate neutrons and create fusion neutron sources. And it'll be in the future, especially with this new facility with 3 petawatt lasers, we'll be learning more ways and better techniques to generate fusions. And then hopefully one of those techniques will be viable for a fusion power plant. But we're still very much R&D here at Colorado State.
Thank you.
Other questions for Jaden? So I have a question on some of the fabrication stuff that you're like working on for making these targets. So you talked about, one of your future goals is making like a thinner slab. Can you comment on some of the difficulties right now you're facing right now in making a thinner slab?
So our process of extrusion, you would need a thicker slab just to ensure that all of the polyethylene flows through the AO wafers. But varying the amount of polyethylene would you could try making different wires with that.
And with, the fabricating these targets, I mean, right now, as you said, you're in the R&D process, but, eventually, is there like an idea on how to speed up the making of these targets? Like I know, General Atomics, I mean, it's a very different scheme, right? But they're, having these like droplets trying to make them super, super fast. Obviously that's not something you're there yet, but what is like the slowest process in your fabrication technique? Is it the extrusion or how can it be sped up a little bit?
So our process, it takes about maybe a day to make. We make 3 of these templates. The longest part is the supercritical dryer because we only have one of them. But it's more of I don't know. Each template that we create has maybe like 30 shots on it. And if we create 3 of them a day, that's like 100 shots per day that we can make.
And is it 30 shots like just because of the size of the target? Like you could just hit different parts of the target?
We cut them up.
Okay.
And
Okay.
mount them each individually.
I see. Well, that's really cool.
Yeah.
Other questions for Jaden. They can be simple. If they're super hard, you can always, again, pass them along.
Jaden, a quick question, Richard Sandberg here. Is the thought, so I've seen some different schemes for marble fusion, but I was assuming that one of the properties of these nanowires would be direct drive fusion, not necessarily to generate neutrons, but just because you could get to such a high ionization state and get to a hot, dense plasma. Has there been any thought to coat the capsules with nanowires?
No, that's a great question, especially because the nanowires have such a high rate of absorption. That's definitely something we'd like to look into.
Has there been any efforts to do this extrusion or this growth on spherical surfaces, or not yet, or can't tell us?
Not yet.
Okay. Very cool. Thank you.
So with that, I would like to thank Jaden again for giving such an excellent talk. I learned a lot about the nanowires, and I hope others have as well. So thank you, Jaden. Our speaker next month will be Muzamal from Texas A&M, and he'll talk about some of the simulation work for stimulated Brillouin scattering. So we're going to turn back a little bit more on some of the laser driver efforts. And if anyone else is interested in being a guest speaker at any point, please feel free to reach out to me, and we'll upload this talk as soon as we can. So thank you again, Jaden, and have a wonderful afternoon, everyone.
Thank you.